everyone. Welcome to the presentation for the course Artificial Intelligence Foundations and Applications for the autumn semester 2022-23. I, Aman Kedia, along with my three other teammates, Saurabh, Prince, and Amrit, extend our warm greetings. The topic of our presentation is Survey on Path Planning Algorithms and their applications. So let's get started. Next slide, please. Now, here is the overview. It starts with the introduction to path planning, then modeling the environment of an autonomous agent, then different algorithms used for the purpose of path planning, and at last, the real-life applications ending with a concluding note. Next slide. So let's start with the introduction. I'm pretty sure you must have encountered some sort of autonomous agent at some point of time. Autonomous robotics field has just changed the way things have worked in this world for centuries. For example, going deep down into the earth using machines, or be it exploring other planets using rovers, or even the virtual games that we play on our PCs. It has saved us years of time and manpower, but with these autonomous power comes huge responsibility on us to avoid risk. For example, a robot working at a construction site, if goes out of control, can cause severe accidents, and path planning is the another of our responsibility. So here for this presentation, we are focusing on the problem of path planning and its algorithm. Its task is to identify a sequence of control inputs that will move a robot from its beginning state to one of the target states given a description of the robot's dynamics, a description of the environment, an initial state, and a set of goal states. And it must also abide by the laws of the environment, such as avoiding any obstacles or obstructions. Algorithms used for path planning often aim to find the best path and, if not the best, at least achieve an acceptable approximation of it. On the right, you can see a beautiful presentation of what wonders path planning algorithms can do. The red square is the pursuer robot and the green is the target one. Algorithms known as RRT, which we'll discuss in detail in a while, is being used here. The constraint is that the red square must not touch any black obstacle and finally reach the green target. Next slide, please. Now, moving ahead, here are some characteristics of effective path planning algorithms. First, it must always be able to identify the best path. It should also be scalable to dynamic environments. It must be consistent with the selected self-referencing strategy, and it should have minimum complexity, data storage, and reasonable computing time. Now, let's look into the types of path planning algorithms. It can be classified into two types in general, global and local. In global path planning, the algorithm creates a full path from the starting point to the final endpoint before the robot begins to follow the intended trajectory. While in local path planning, the robot has the capacity to create a new course in reaction to the environment changes in real time. The algorithm traverses path using the data from the nearby sensors. Also, it can be seen in the image on the right. These can further be divided into four different subgroups with the subgroups within them. But let's keep that discussion first. As humans, our path on plain terrain is different from that in the hilly regions, isn't it? So we must acknowledge the fact that to plan an optimal path, we must have a solid understanding of the environment of the agent and their interaction. For this, we need to construct environment of our agent. Here, we only use metric mappings to construct graph. We can construct graphs in two ways. First, by dividing the surface into cells using tessellations, and other by the roadmaps to portray the environment. Tessellations can be done using regular and irregular grids. Next slide, please. As shown here in the first three images, which are regular grids, its main advantage is the simple indexation of each node, which is translated into quick access to any of them and an optimized way to store them in memory. Irregular grids, such as the one depicted in the figure 2D, allow the better adaptation uh, to the grid to the terrain features. A roadmap is made up of network with nodes and edges as represented in the last two images, the Voronoi roadmap and the state lattice graph. Next, my teammate Prince Raj will take you through some popular advanced algorithms for path planning in detail. Over to you, Prince.
Uh, Thank you, Aman. I'll discuss search-based path planning algorithms. I'll first start with Dijkstra and its variants, which are used in applications such as Google Maps and other traffic routing algorithms. It works for the case when the edge costs are between 0 to infinity, since it does a lot of blind searches to find the shortest route. To overcome this, I'll discuss other heuristic-based algorithms such as A star. A star is used for shortest path evaluation based on the information regarding the obstacles present in the environment. And the shortest path evaluation for the non-static environment is a two-level problem, which comprises a selection of feasible node pairs and shortest path evaluation based on the obtained feasible node pairs. Both of the above mentioned criteria are not available in a dynamic environment, which makes the algorithm inefficient and impractical in dynamic environments. To do path planning in dynamic environments, the D-star algorithm is discussed. The Dijkstra algorithm operates by figuring out the shortest path between the source and vertices among those that are nearest to it by keeping the new vertices in a priority min queue and storing just one intermediate node. It can only determine the shortest path uh, to the next closest vertex. Dijkstra finds the shortest path in an acyclic environment and can calculate the shortest path from a starting point to every point. For path planning, the conventional Dijkstra algorithm uses a greedy approach. It is employed to locate the graph's shortest path without formally paying regard to the pragmatism of the answer. It is only interested in finding the shortest path. When creating plausible shortest paths incurs large cost, the modified Dijkstra algorithm seeks alternatives. There have been many improvements to the vanilla Dijkstra algorithm, which works for different cases. The modified algorithm introduces another component to the classic algorithm uh, in the form of probabilities that define the status of freedom along each edge of the graph. Next. So this is the flow chart of Dijkstra algorithm. Next, other than Dijkstra algorithm, which only works in the case for of positive edge graphs, two other algorithms are Bellman-Ford and Floyd-Warshall algorithm. The Floyd-Warshall algorithm computes the shortest path from each node to every other node, whereas the Bellman-Ford algorithm computes the shortest path from a single source vertex to all of the other vertices in a weighted graph. In these two cases, edges can be negative too, and these are the flow charts for both. The flowed Warsaw algorithm uses adjacency matrix. Next. Now, the A star algorithm is like Dijkstra algorithm. In that it can be used to find the shortest path. A star is like greedy based first search in that it can use a heuristic to guide itself. In the simple case, it is as fast as greedy based first search. The key to its success is that it combines the information from that greedy based first search and Dijkstra algorithm employ, prioritizing the vertices that are close to the starting point. When discussing A star, the terms Gn and Hn respectively stand for the exact cost of the path from the starting point to any vertex n, and the heuristic estimated cost from the vertex n to the destination. The A star algorithm is a heuristic algorithm that seeks out the best course of action using heuristic information. The A star must look for nodes on the map and set the proper heuristic functions such as Manhattan distance, Euclidean distance. Finding the shortest route from a crowded parking lot to an empty space uh, is one straightforward application of the A-star algorithm. The shortest path to the vacant spot is acquired after the global optimal solution, which is produced in the hierarchical A-star algorithm, which divides path searching into few phases. A weighted sum is utilized in conjunction with the heuristic in the revised hierarchical A-star algorithm, which further improves the method by employing the optimal time as an evaluation index. Next. So this is the pseudocode for A-star algorithm, which finds the node with minimum fn, which is gn plus hn. Next. Now, D-star algorithm efficiency in path planning is partially known and changeable situations is becoming increasingly important. For example, for driverless vehicles, the D-star or dynamic A-star algorithm is used to create a collision-free path among moving obstacles in order to overcome this challenge. D-star is an informed incremental search algorithm that repairs the cost map partially and the previously calculated cost map. The algorithm is known as D-star because it is similar to A-star but is dynamic in that the R costs can change as the solution path is traversed. It is guaranteed to be optimal as long as the traverse is appropriately coupled to the replanning procedure. The only portion of the path that leads to where the robot is right now is where replanting is required. The areas that the robot may use are kept within the scope of the partial optimal cost map. Additionally, the states that are likely to result in a new optimal paths are utilized to reform the cost of the map, which will be somewhat limited and re-entrant. D-star stabilizes the criteria for deciding whether repairs will be halted due to the discovery of a new path or confirmation that the previously discovered path is still the best option. Therefore, D-star strategy is used to describe a strategy that is computationally efficient, highly memory active, and operable in unbounded environments. Next. This is the pseudo code for D-star light algorithm, and this is the comparison among these all. Actually, currently in the industry, we use D-star light algorithm, which improves upon LP-star, which is a lifelong planning A-star, and there is another improvement on D-star light, which is enhanced daylight star algorithm. So we can discuss this later. Over to you, Saurabh.
Thank you, Prince. So now we will discuss the random sampling based path planning algorithms. So search based algorithms requires explicit representation of the obstacles in configuration space, which is very inefficient in terms of memory as well as time requirements. Sampling based algorithms avoid this and are probabilistically complete, which means that as number of sample points goes to infinity, the probability that the planner fails to find a path, if one exists, asymptotically approaches to zero. Now let's discuss a few famous and fast sampling based path planning algorithms. We will start with probabilistic roadmaps, in short, PRM. So it is a network graph of possible paths in a given map based on free and occupied spaces. The algorithm is as follows. So a random node is generated in the C space. Then the system checks then the system checks whether this node lies in the free space or not. That is, whether this configuration intersects with an obstacle or not. And if the node is in free space, it is added to the graph. This newly generated node is then connected to the closure nodes through straight lines, and the system then checks if the connection between two nodes lies in free space or not. And for example, here the red connection does not lie in free space, and hence it is removed. After getting a complete graph, we add start and end node and apply algorithms like Dijkstra and A star to find the shortest path. Now we will discuss one of the most famous random sampling algorithm, that is rapidly exploring random trees, in short RRT. It is aimed at single query applications, which means that given a pair of start and goal nodes, it generates tree of nodes from scratch. The difference between PRM and RRT is that PRM constructs a graph and RRT constructs a tree. Initially, the tree has only start node, and at each iteration, a random point in configuration space is chosen, and if its connection to the nearest vertex does not cross any obstacle, it is added to the tree. And then the iteration is stopped as soon as the tree contains a node in the goal region. This algorithm is one of the fastest planning algorithms with only one downside, which is that it does not return shortest path between start and goal node. Hence, to address this issue, optimal RRT or RRT star was proposed. It is built upon RRT algorithm with two key additions. So while building the tree, RRT star records the distance each node and each node has traveled relative to its parent node, and this distance is referred as the cost of the node. As usual, a random point is sampled and then a neighborhood of nodes in a fixed radius from new node is examined. So if a node with the cheaper cost than the proximal node is found, cheaper node replaces proximal node. So it is evident here that this particular node is the proximal node. But since start node is cheaper in cost, the newly added node makes connection with the start node. And then the second difference RRT star adds is the rewiring of the tree. So when the new nodes are added, the neighbors are checked if being rewired to the newly added vertex will make their cost decrease. If the cost does indeed decrease, the neighboring nodes are rewired to the newly added vertex. For example, in this case, the newly added orange node decreases the overall cost of this node. And if it is connected with the overall cost of this node, and if it is connected with the orange node, the overall cost of it decreases, and hence the rewiring of connection takes place. And and similarly, we generate the newly sampled nodes, and once we reach to the goal, the algorithm terminates. So due to examining neighboring nodes and rewiring the graph, RRT star takes more time than RRT to return the solution. Now Amrit will discuss meta-heuristic algorithms. Over to you, Amrit.
Thank you, Saurabh. Discrete search-based and random sampling-based algorithms require a substantial amount of CPU performance and memory. Meta-heuristic algorithms help tackle such problems. They are able to cover a large search space using minimal memory and CPU resources. They are also able to adapt to changing environments. Meta-heuristic algorithms attempt to find the best feasible solution out of all possible solutions for a given optimization. Moving to the next slide, the first type of meta-heuristic algorithm that we are going to see is genetic algorithm. The genetic algorithm is analogous to biological natural selection process in which the best genes are transferred from parents to offspring. Genetic algorithms can be applied to dynamic path planning problems. An interesting example of this would be robots playing football. All possible solutions are represented as individuals of a population with each gene representing a parameter. A new generation is found by selecting the best individuals, and genetic operators like crossover and mutation are applied to explore additional solutions. Each offspring from the new generation is tested with a fitness function. The important characteristic that makes genetic algorithms suitable for solving these kinds of problems is that it is an inherently parallel search method and has the capability to search for the optimal path in a given environment. One disadvantage is that the solution found for the problem may not always be the global minimum. Now, moving on to the second type of meta-heuristic algorithm, it is ant colony optimization algorithm. Ant colony optimization algorithm is based on the way ants find an optimal collision-free path to the food source using pheromones. The For example, path planning of autonomous ground vehicles and aerial vehicles, evacuation planning in hazardous environments, and infrastructure networks like Tokyo railway station. The algorithm is based on pheromone deposits, which determine the probability of an artificial ant going from one node to another node. The more the pheromone value, the higher the probability that the ant will take the path. The striking features of ACO algorithm are positive feedback helping in discovering a goal rapidly, distributed computation avoiding premature convergence, and greedy heuristics aiding in finding a goal in the early stages. Now, moving on to the next slide, it is the next type of algorithms that are learning based algorithms. These methods need to be trained by a supervised using ground truth data. The training process essentially encodes map information in internal representation, a deep neural network. At test time, the methods can handle environments sharing similar settings with the training. In essence, learning-based planners are data-driven and can be limited to the environments that are present in the training data. Now let us see some of the applications to which the first picture, as we can see, is the Mars rover. So path planning algorithms can be used for pathfinding purposes. The second picture, as we can see, is in video games where the computer must guide simulated adversaries around the map. The third picture is the Google map. So we also use path planning algorithms to find a route in a map. Moving on to the next slide. Path planning algorithms are also used for infrastructure planning, like control plants and busy railway stations. They are also used in timetable scheduling, as we can see in our ERPs. Now, moving to the last and final slide. Recent years have seen the rapid growth of artificial intelligence in driverless vehicles and other automated mobile systems. As a result, the amount of research into path planning has increased dramatically. In this report, we have tried to present several widely used path planning algorithms. In each section, we covered the brief methodology of all the algorithms as well as their advantages and disadvantages. We came to see that for a given map, algorithm A star is a strong performing option for static environments, making it suitable for use in embedded system deployment. We also saw that some of the limitation of bio-inspired algorithms is that they do not have excellent results in real-time path planning, as they have a possibility of becoming stuck in local minima. Though not exhaustive, this coverage provides a simplified summary for these techniques, their use cases, and trade-offs. With this, I would like to conclude. Thank you.